When dealing with multi-tap current transformers, or CTs, it's important to understand how different configurations of unused terminals can affect their operation, especially in the context of differential protection schemes. The core issue revolves around the behavior of the magnetic field within the CT and the resulting current flow in the secondary winding. When the unused terminals of a multi-tap CT are left open, the magnetic field generated by the primary current is not completely balanced. This imbalance leads to a voltage being induced across these open terminals. This voltage, in turn, can drive a current through the secondary winding of the CT. If this current is significant enough, it can be detected by the differential relay, causing a false trip. The differential relay, designed to protect the transformer by comparing currents on either side, misinterprets this induced current as an internal fault. Conversely, when the unused terminals are shorted together, a significantly different scenario unfolds. Shorting the unused terminals effectively balances the magnetic field within the CT. This balance field minimizes the voltage induced across the open terminals, ideally reducing it to zero. Consequently, minimal to no current flows in the secondary winding due to this effect, and the differential relay remains inactive, reflecting the absence of a true fault condition. The grounding of the CT secondary is another crucial aspect of safe and reliable CT operation. Grounding provides a designated path for current to flow in the event of a fault. Without this grounding, the voltage across the open terminals of the CT, whether they are intentionally left open or become open due to fault, can escalate to dangerous levels. Such high voltages pose a risk of damaging the CT itself, other connected equipment, or even creating a safety hazard. The grounding connection ensures that any fault current has a low impedance path to ground, limiting the voltage rise and facilitating the prompt operation of protective devices. To visualize this, imagine a multi-tap CT connected to a power transformer. The primary winding of the CT encircles the high voltage conductor, sensing the current flowing through it. The secondary winding, with its multiple taps, provides different current ratios for measurement or protection purposes. The unused taps, if left open, become susceptible to the magnetic imbalance described earlier. Shorting these taps creates a closed loop, effectively nullifying the voltage buildup. Now let's delve into the practical implications of these principles. In a real-world scenario, such as the one involving a transformer differential protection scheme, the incorrect handling of unused CT taps can have significant consequences. The phenomenon observed, where the differential relay tripped at 30%, indicates that the current induced by the open-circuited taps was substantial enough to be interpreted as a fault. The event recorder's behavior further supports this, showing zero current on the one high-side CT when the taps were shorted, and registering current only after the differential relay tripped and the circuit was opened. The resolution of the problem by relocating the ground wires and unshorting the unused terminals highlights the sensitivity of the system to these configurations. The fact that the primary CT started reading correctly after these changes underscores the importance of understanding the underlying electromagnetic principles. Several factors contribute to this behavior. Firstly, the magnetic core of the CT is designed to operate within a specific range of flux density. When the unused taps are open, the flux distribution becomes uneven, potentially pushing the core into saturation in certain regions. This non-linear behavior exacerbates the voltage and current induction in the secondary winding. Secondly, the impedance of the differential relay plays a role. If the relay has a relatively low impedance, it will draw more current from the CT secondary, making it more susceptible to false tripping. Conversely, a high impedance relay would be less sensitive. Thirdly, the physical layout of the CT and its associated wiring can influence the amount of induced current. Long, unshielded wires can act as antennas, picking up electromagnetic interference and contributing to the overall noise level. The common practice of shorting CT secondaries is not merely an arbitrary rule, it is a fundamental principle of CT operation that ensures both accurate measurement and safe operation. Shorting the secondary provides a low impedance path for the induced current, preventing the buildup of hazardous voltages. This is particularly critical when the primary winding is energized and the secondary circuit is inadvertently opened. The open circuit can result in extremely high voltages that can damage the CT insulation, create arcing, and pose a significant safety risk to personnel. The absence of current readings on the one primary CT when the unused taps were shorted suggests that the shorted taps were effectively shunting the current away from the relay. This is consistent with the principle that current will always flow through the path of least impedance. When the taps were open, the impedance of the secondary circuit increased, forcing more current to flow through the relay. Therefore, several guidelines and best practices should be followed when dealing with multi-tap CT. Firstly, always ensure that unused taps are properly shorted together using a dedicated shorting block or terminal. Secondly, verify that the CT secondary is adequately grounded to provide a safe path for fault currents. Thirdly, use shielded wiring for CT circuits to minimize electromagnetic interference. Fourthly, select CT with appropriate burden ratings to match the relay impedance. Fifthly, regularly inspect CT and their associated wiring for any signs of damage or degradation. In addition to these practical considerations, it is helpful to understand the equivalent circuit of a CT. The CT can be modeled as an ideal transformer in parallel with a magnetizing inductance and a core loss resistance, and in series with a secondary winding resistance and leakage inductance. The magnetizing inductance represents the inductance of the core, while the core loss resistance accounts for the energy dissipated in the core due to hysteresis and eddy currents. The secondary winding resistance and leakage inductance represent the impedance of the secondary winding. When the secondary circuit is open, the magnetizing inductance becomes the dominant impedance, leading to a high voltage buildup. When the secondary is shorted, the secondary winding resistance becomes the dominant impedance, limiting the voltage. The choice of CT ratio is also crucial for accurate and reliable protection. The CT ratio should be selected such that the secondary current is within the operating range of the relay under normal load conditions. The CT must also be able to withstand the maximum fault current without saturating. Saturation occurs when the magnetic flux in the core exceeds its maximum limit, leading to a nonlinear relationship between the primary and secondary currents. Saturation can compromise the accuracy of the protection scheme and may even cause the relay to maloperate. Modern digital relays often incorporate features such as CT saturation detection and compensation to mitigate the effects of saturation. These features use algorithms to estimate the degree of saturation and adjust the relay settings accordingly. It is essential to consult the relay manufacturer's documentation for specific recommendations on CT selection and settings. Furthermore, regular testing and maintenance of CT are essential to ensure their continued reliability. Testing should include insulation resistance measurements, ratio verification, and polarity checks. Insulation resistance measurements verify the integrity of the CT insulation. Ratio verification confirms that the CT ratio is within acceptable limit. Polarity checks ensure that the CT polarity is correct, which is crucial for proper operation of differential protection schemes. In summary, the behavior of multi-tap CT with open or shorted unused terminals is governed by fundamental electromagnetic principles. Open terminals create a magnetic imbalance, leading to voltage and current induction in the secondary winding. Shorted terminals balance the magnetic fields, minimizing these effects. Grounding the CT secondary provides a safe path for fault currents. Following best practices for CT selection, installation, and maintenance is essential for ensuring accurate and reliable protection. Keep in mind that the information provided is a general overview and specific applications may require further analysis and consideration. Always consult with qualified engineers and refer to relevant industry standards and guidelines. Furthermore, understanding the specific characteristics of the CT model being used is vital. Different CT designs may exhibit variations in performance and sensitivity to open or shorted taps. Consult the manufacturer's specifications and application notes for detailed information. Additionally, consider the impact of external factors such as temperature and humidity on CT performance. Extreme temperatures can affect the CT insulation and magnetic properties. High humidity can lead to corrosion and degradation of the CT components. Regular inspections and maintenance can help identify and mitigate these issues. Also consider the burden impedance connected to the CT secondary. The burden impedance is the total impedance seen by the CT secondary, including the relay impedance, wiring impedance, and any other connected devices. The CT must be able to supply the required current to the burden impedance without saturating. The burden impedance should be within the CT specified range. Exceeding the CT burden rating can lead to inaccurate measurements and potential damage to the CT. The location of the grounding point on the CT secondary can also affect the performance of the protection scheme. The grounding point should be located as close as possible to the relay to minimize the impedance of the grounding path. A high impedance grounding path can lead to voltage buildup on the CT secondary and may compromise the operation of the protection scheme. Modern protection relays often incorporate advanced features such as adaptive protection and fault location. Adaptive protection automatically adjusts the relay settings based on the system conditions. Fault location uses advanced algorithms to pinpoint the location of a fault. These features can improve the reliability and performance of the protection scheme. In addition to the technical aspects, it is important to consider the human factors involved in CT operation and maintenance. Proper training and documentation are essential to ensure that personnel are familiar with the CT and their associated protection schemes. Clear and concise procedures should be developed for CT installation, testing, and maintenance. These procedures should be readily available to personnel and should be followed consistently. Regular audits of the CT protection schemes can help identify any potential problems or areas for improvement. The audit should include a review of the CT settings, wiring, and grounding. Any identified issue should be addressed promptly. In conclusion, the successful application of multi-tap CT requires a thorough understanding of their operating principles, best practices, and potential pitfalls. By following the guidelines and recommendations outlined, engineers and technicians can ensure the safe and reliable operation of these critical components of power systems. Remember to always prioritize safety when working with electrical equipment. Follow all applicable safety procedures and use appropriate personal protective equipment. Never work on energized equipment unless you are properly trained and authorized to do so. Electrical work can be dangerous, and even small mistakes can have serious consequences. Therefore, always exercise caution and seek assistance from qualified professionals when needed. Furthermore, continuous learning and professional development are essential for staying up to date with the latest advancements in CT technology and protection schemes. Attend industry conferences, workshops, and training courses to enhance your knowledge and skills. Read technical publications and journals to stay informed about the latest research and developments. By investing in your professional development, you can ensure that you are equipped to address the challenges of modern power systems. Always remember that the reliability of the power system depends on the proper functioning of its individual components, including CT. By paying attention to the details and following best practices, you can contribute to a more reliable and sustainable power grid. Also, consider the use of fiber optic CT. Fiber optic CT use optical sensors to measure the current flowing through a conductor. Fiber optic CT offers several advantages over conventional CT, including improved accuracy, wider bandwidth, and immunity to electromagnetic interference. Fiber optic CT are becoming increasingly popular in high-voltage applications. Another aspect to consider is the use of CT in renewable energy systems. Renewable energy systems, such as solar and wind power plants, often use CT to monitor the current flowing through the system. The CT are used to protect the system from overcurrents and to provide data for monitoring and control purposes. The selection of CT for renewable energy systems should take into account the unique characteristics of these systems, such as the intermittent nature of the energy source and the presence of harmonics. Furthermore, the use of smart CT is gaining traction. Smart CT incorporates advanced features such as digital communication, self-monitoring, and remote control. Smart CT can provide real-time data on the CT performance and can be used to improve the reliability and efficiency of the power system. Smart CT can also be used to detect and prevent CT failures. Finally, It is essential to stay informed about the latest industry standards and regulations related to CT. Standards such as the Institute of Electrical and Electronics Engineers, or IEE, C57.13, standard requirements for instrument transformers, provide guidance on the design, testing, and application of CT. Compliance with these standards is essential for ensuring the safety and reliability of the power system.